ownership of the data sharing component to make this sustainable. So I've discussed quite a lot of hurdles and barriers, but I'm hoping that I've given you an idea of how we are overcoming them. And I've given you a sense that within DDD Africa that we, like young Tumi over here, are not scared of some hurdles. And Amanda and Prince will now share some insights on how we are using exome sequencing for impact within DDD Africa.
Thank you very much, Nadia, for this excellent overview. So now we move to Kinshasa, DRC. And I will all remind you that you should follow the Congolese team in the football because they're just wonderful. Prens, the word is to you. You're stuck. So you should open your PowerPoint, and then there you will see share this window. Yeah, I will ask Amanda to start, and in the meantime you can maybe contact Nicolas to know and send it to me, okay? Yeah. Yeah, I'll ask Nicolas. Nicolas, can you share Prince?
Yes, I'm opening.
Yeah, he's stuck.
Oh yeah, but can he talk though? Does he have sound or not?
Prince, can you talk?
Yeah, let's see if your sound is okay at least.
It is muted.
Yeah, Prince can't open his. He's muted and he cannot unmute, apparently. So maybe let's start with Amanda, and in the meantime, maybe Prince and Nicolas, you can try to sort out what's going on.
Yeah.
So Amanda Krause, she's from the Witwatersrand University, the National Health Lab Service, and she will talk about the South African experience in DDD Africa.
Yes, second. So doing very strange things. A second. It's done a very strange thing. Hold on.
It's okay. We see your screen.
Yes, we can see it now.
Yeah.
You can see my screen?
Yeah.
Okay,
second slide already. Yeah.
Okay, I can't see my screen is part of the problem. Let me think how I can do this.
you should go to your presentation, and you just we see your presentation, and you just go to your presentation.
And I know, but I can't change the slides then.
Yes, yeah, you should be able to do so in your presentation.
I'm going to just stop sharing and share again. Give me a second. Oh gosh. It's gone into a very strange. It's not what it did before, but let's see if we can do it. Okay, let's try again. Okay. I'm hoping that looks better.
No. No, we see the two slides.
Still.
Yeah.
Okay. Thought we had this sorted. Do you want to allow me? This is very annoying because just earlier on it worked fine when I.
Yeah. So you go to your presentation, and there you can see share this window. And stay in your presentation, and then go to presentation mode.
So from here, it's not allowing me to share it. It's going to this PowerPoint Live, which looks very odd. It's not what it did earlier on.
No.
Mm-mm.
Okay, that's fine.
What can you see?
Yeah, yeah.
Can you see all the slides at the bottom? Is that what you're seeing?
If you wish, I can move your slides.
This is so annoying.
If
okay,
you just
so let
say
me
next slide,
open
I'll
my
do it.
presentation on my other computer.
But we see it, Amanda. We see your presentation.
Okay.
And if you say next slide, I can.
Okay, so the problem is I just need to be able to see my presentation.
Okay.
Okay, I can see my presentation. You can see my presentation.
Yes.
Okay. All right. But I just have to say next slide as I change the slide.
Yes, please.
Okay, so good afternoon, everybody, and apologies for the technical delays. That didn't happen on the practice round. So I'm going to present some of I'm a medical geneticist in Johannesburg at the University of the Witwatersrand. And so Prince and my presentations are really looking at some of the clinical aspects in slightly different ways. His from the DRC and mine from South Africa. So there's some things that are a little bit switched around, but we'll manage. But I think one of the important messages, you've heard some of the challenges perhaps, and some of the reasons why we established the DDD Africa project. But I think that for those of us who've worked on it, there've been some enormous successes for us in our learning and in our understanding of developmental disorders in Africa. But I think importantly, maybe to justify sort of the importance of it for populations around the world where there are many African patients living in many other countries, and perhaps some of our findings around new diseases which may have been not as well profiled and that we've identified. So I'm going to go through some of those examples, obviously not very many of them, and maybe just to start with a slide that you already have seen, but just really to emphasize the multi-pronged DDD project or DDD Africa project, very heavily modeled on DDD UK, but which has multiple components. Nadia's already referred to some of the technical components perhaps, and our training sort of intentions, but I'm going to focus a little bit more now on the clinical and some of the patient implications. So the DDD Africa cohort has two main sort of sampling sites. The one is the DRC, which hopefully Prince will share shortly. And the second one, site is the South African site, largely based in Johannesburg, but also now I can't point, but okay. Also with some recruitment from KZN. So the size of the, on the map doesn't completely reflect the size of the cohort. Our cohort's a little bit, a few more males than females, and aimed for trios largely, but something of a challenge in our local situation. So about half trios and half duos with a few singletons, and then the distribution of our cohort largely young patients, but extending quite a lot as well. And perhaps illustrating that some of these patients had been around for many years waiting for a diagnosis before we recruited them into DDD. So next slide, Kun, I'm hoping you're keeping up with me. But
do you see the slides? I got a message. Do you see the slides moving?
No.
No. It's still the first slide, Amanda.
So I wonder if this is so annoying. What should I try and do? Because I don't actually know what to do. Let me see if I can change. I can do it this way.
Yeah, I think now I'm sharing now. Should be fine or not? Can everyone see the second slide?
Yeah.
Oh, no, the third, right?
Go to the next slide. I'm really confused because I'm not seeing the shared slide is the challenge.
The third slide, Nicholas? Yeah.
Yeah, is it this one?
No.
Oh, the one before.
Yeah, go up.
So can everyone see the slides or not?
No slides now.
No slides. Oh no.
No, we don't see any slide.
Can we try and share again?
No.
This is so frustrating.
I
It's
don't know what's
because we
going on with my
cursed
computer. I think it's like,
Teams, Kun.
Yeah. That's why we use Zoom. Now I see it. Yeah.
yeah, now it's good.
Go to the third.
Third.
Next. No, we don't. No.
No, next one.
No, we still see the second slide.
That's
Very
that's weird.
frustrating.
Yeah, that's weird. Yeah, don't know what's going on with my computer either. I only know that
I'm going to try to do what I did earlier on.
Yes.
Maybe
maybe I'll try again with the online.
Nicholas,
version.
can I try? Because earlier
Oh, yeah,
on,
sure.
I was able to share on the double screen. It was just that you were seeing the two screens. So maybe that's better
Well, it
than
doesn't matter. I
nothing.
think. Yeah.
Okay.
Let's see if I can get it to presenter mode. Maybe I can't. What can you now see my slides? If not,
Yeah.
But they're not in presenter mode.
Not in presenter mode.
But you can see them. Maybe that's good enough.
Yeah. Okay.
Okay, I apologize. Okay. So so maybe this is the slide that you didn't see, just describing the South African cohort. but to say that we've collected our cohort of 358 probands who largely represent a group predominantly with all with developmental disorders, many with developmental delay, and other structural abnormalities, and really to sort of justify our what's already been said today, which is that many of the patients in our country, in our system, remain undiagnosed because of the lack of genomic diagnostic services or even more basic diagnostic services. And so one of our logics of embarking on this project was to try and reach a diagnosis for many of these unresolved patients, something not unfamiliar to many of you. So in broad summary, based on our exome analysis only, but including SMV and CNV analysis, we currently have a yield of around just around 40%, with now 143 of our 358 probands having diagnoses based on exome analysis so far. So I wanted to just sort of highlight a couple of things. I know that it's not easy to see the slides, and similarly to many other developmental disorder projects around the world, there's obviously many different genes which have been implicated in different families, some of them similar, some of them different. I wanted to just highlight a couple of them that I'm going to talk about. So perhaps ARID1B, Coffin-Cyrus syndrome, or one of the genes for Coffin-Cyrus syndrome, one that is repeatedly reported as a common diagnosis in many developmental delay series, CHD7 as well, SMARCA2 perhaps, but to highlight two other genes that I'm going to talk about in a little bit more detail, PGAP3, which is a gene rare in non-African cohorts, but where we have an interesting common African mutation, and potentially a similar scenario with VPS13B, one of the Cohen syndrome genes. So really to sort of summarize some of the really key lessons and things that I'm going to talk about, but confirmation of diagnosis, something that is, again, I think recognized as being important for families and doctors because it determines management, but also understanding unusual mechanisms of disease in some families, some unrecognized founder mutations, again, a bit counterintuitive that in a diverse African population, we sometimes see deep African founders, and some of those are unrecognized until this point. We haven't really embarked in any detail on looking at the African phenotypes, but I'll come to it in a minute or two, and some of the expanded phenotypes as well. So I wanted to start really with a condition that many of the medical geneticists will be familiar with. So Coffin-Cyrus syndrome due to ARID1B mutations, and people working in developmental disorders will be familiar with ARID1B as a gene that is often found in cohorts of children with developmental delay, including in our DDD South African cohort, where we have 6 positive cases, 4 with SNVs and 2 with CMVs involving the ARID1B gene. I think one of the important lessons here that's worth stating, even though it's almost an obvious, and that is that if you work in an environment where only clinical diagnosis is available to you, then when you're making a clinical diagnosis that is correct or incorrect, you don't always know about it because you haven't got the molecular confirmation. And so this is a common condition, but none of these patients had been given, maybe not all, and none of them, but almost all of them hadn't been given a clinical diagnosis before the DDD Africa results came out. And again, I think the importance of the research and the diagnosis in expanding the knowledge of the practicing medical geneticists to expand their service to patients is really one of the important but maybe very basic lessons that we've learned from DDD Africa. So I think there are many lessons. Maybe this is sort of the most fundamental of them, but I think still this obviously doesn't only apply to ARID1B, but to a number of the other conditions as well. So I wanted to go to another common condition, which again, we've identified 4 patients with CHD7 variants in our cohort. Again, a phenotype that is well described and well characterized, familiar to many as in its most severe form, the charge syndrome. But importantly, CHD7 is a broad phenotype. Not all patients fulfill diagnostic criteria for charge syndrome. And importantly, one of the key features used to make a clinical diagnosis, at least, of charge syndrome is finding hyperplastic semicircular canals, which requires a temporal bone CT scan to do so. So without the suspicion or without the availability of the scan, it's very difficult to identify the semicircular canals, and therefore it's very difficult to make a diagnosis. So these patients remain with a suspicion, in some cases, of a charge or CHD7 related disorder, but without a confirmed diagnosis. And for me, this is one of those where the diagnosis makes a big difference, because there are some very clear clinical guidelines which are important in terms of the endocrine follow-up of these patients, which they wouldn't otherwise get if they didn't have a CHD7 diagnosis. So again, the importance of the diagnosis in defining their very directed and careful follow-on management. So going from there to one of the perhaps counterintuitive findings, so a variant or a condition not described by us, but had been described in the South African cohort, or in South African patients previous to DDD Africa, but one that we clinically had not diagnosed before DDD Africa in our cohort, and have 5 patients in the DDD Africa cohort who are all homozygous for the same mutation in PGAP3. It's a lysosomal storage disorder. It's an unusual gene for this, for what is sometimes termed Mabry disease, hyperphosphatasia with impaired intellectual disability, in this case type 4, with severe intellectual disability, some fairly characteristic features, particularly the absent speech, the hypertonia, and some quite significant clinical complications, often picked up or diagnosed incidentally by their high ALK-Phos levels related to some bone metabolism. Interestingly, brachytelephalangy, which is a commonly described feature in many of the PGAP3 patients described around the world, is not found in our patients, again, perhaps suggesting some subtle differences in the phenotype. But again, I think seeing homozygosity in an African context is not something we intuitively think about, but are increasingly aware of deep African founder mutations, which are not necessarily described in other areas of the world, but which change our recognition and potentially make for common conditions that can be easily tested for. So similar to that, interestingly, we have found 3 patients with Cohen syndrome, all with the same variant in the VPS13B gene. So they are not all homozygotes. 2 of them are compound heterozygotes. But again, a suggestion, perhaps because of a common variant in unrelated patients, that there may be a common African founder variant here, and that, again, may have implications for our recognition, diagnosis, and testing. So similar to other cohorts, finding dual diagnoses is something that we have also experienced. I'm not going to speak about these in any detail. Prince, when he shares his talk, will talk a little bit about dual diagnosis as well. So I wanted to just continue a little bit beyond this and say that obviously the exome data has been very helpful, and thus far we have confirmed diagnoses in about 40% of our patients. I didn't say right at the beginning that our yield is slightly lower than the yield in the DRC. And one of the reasons for that is that many of our patients had actually had some pre-exome CNV analysis, whereas the DRC patients had not. But beyond the exome, we've now moved on to running some of our patients using epi-signatures, and to acknowledge ERN-ITHACA, one of our PhD students, who's currently busy with her PhD. And so thank you, Rasilia, for allowing me to share some of our interesting epi-signature solves, which were not solved on the exome. So I think two interesting ones, one maybe a little bit of a wake-up call in that one of our patients who we'd screened on exome, and he does have some unusual features, which may have been the reason we missed the diagnosis, but came back with a positive epi-sign, epi-signature for Fragile X syndrome, which we've subsequently confirmed. So I don't think that this is a recommendation for the way we should be diagnosing Fragile X syndrome, but perhaps to illustrate the point that it isn't always as clear as we think it is. And so certainly helpful for this patient that we have actually come to a confirmed diagnosis. And maybe to contrast that on the other extreme with a condition that we have not recognized until now, but I think have probably in the last few months now, using the epi-signatures or some research attached to the epi-signature work, initially picked up an epi-signature in collaboration with the EpiSign team in Canada, suggestive of Renew syndrome in one of our patients. And that patient we have now done Sanger sequencing to confirm that that patient now has a RNU42, one of the common RNU42 variants. And we think that this is probably the first patient in Africa reported with an RNU42 mutation. For those unfamiliar perhaps with RNU42, this is a recently described common or relatively common cause of developmental delay and hypotonia, but it's in a gene which is an RNA splicing gene, not in the exome, and so would be missed by exomes, but is, I think, a very exciting finding from our cohort now, and we're hoping to use this to sort of look for more, but proof that we find similar things in Africa sometimes as we do elsewhere in the world, and in an important finding. Sorry. So I wanted to share one other interesting patient who has an interesting epi-signature, a patient with developmental delay, delayed speech, in whom we found a CHAMP1 variant. When we weren't, at the time, we weren't actually very convinced about our variant for various reasons, for various technical reasons. And this patient also had an epi-signature which came back positive for White-Sutton syndrome, typically associated with mutations in the POX-Z gene. And so initially this was one where we were a little bit confused because our patient had a POX-Z epi-signature, but a CHAMP1 variant, until, thanks to Kun made the suggestion that actually CHAMP1 and POX-Z are in a similar biochemical pathway. And so, although this is not verified, we think that actually the epi-signature may pick up variants in other genes in the same POX-Z pathway, including CHAMP1, and that aligns our two findings into an interesting solve or potential solve for our patient and another explanation. So I think, and you've already heard this today, that not only have we made some important sort of impressions on looking at the heterogeneity and the scope of developmental disorders and the genetic underpinnings of these disorders in South Africa, but we thought that it was important to look at how we translate this into extending the research into diagnostic service, both in our own countries, but also further in Africa. And so as a second phase to DDD and I'm very happy to see many of our ITP training colleagues on the call, we have, as Nadia said, identified teams who we hope will sort of champion genomics and clinical genetics in 10 other African countries through a training program that we've initiated and that's been running for the last 3 years with an aim to identify and exome sequence some cohorts identified in each of those countries to extend the reach of the genomic diagnostics, I guess, into these countries. So maybe just to finish off and to say that we learned a lot. We continue to learn a lot from DDD Africa. Certainly has improved our medical genetics practice, has, as Nadia said, made an enormous impact on our capacity building, our development of teams, our multidisciplinary clinical reviews and variant reviews have probably been the most outstanding way that we have extended our knowledge and our reach, and would certainly encourage colleagues from Africa and elsewhere in Europe to join, because I think that we can all benefit from each other in a very positive way through things like those review meetings, but obviously also direct patient benefits in getting answers, some of them after 5 and 10 years of waiting for an answer, and allowing for better management and understanding of the molecular epidemiology. So I just wanted to finish off by thanking the DDD Africa team. It's obviously not a single person study. Even this is a very small part of the team, but is the main team, with the acknowledgements for our funding, which has come from multiple sources, but predominantly from the NIH. And I'm going to hand over, I hope, to Prince to share the DRC component of the DDD Africa clinical findings as the next talk. Prince, are you okay?
Yeah, I'm okay. Okay, this time, okay.
I'm trying to get rid of my talk. Okay.
I mean, it's okay now. It's on first
Yeah.
screen. Okay. Thank you for Amanda for this wonderful presentation, and I'm coming after you to present the result of the DRC DDD study entitled "The Congolese Experience of Introducing Exome Sequencing as a First Diagnostic Text for Explained Developmental Disorder." Yeah, okay. As Kun mentioned before, that this study was this project was initiated in 2018 and brought together these two sub-Saharan African countries. But what I want to highlight here is the for the Kinshasa part. One is that this project was built on the experience of the experience gained in previous study in the domain of developmental disorder, or in the domain of DDD, for example, in 1991 with Professor Lukusa, and in 2015, Amy conducted a study about intellectual disability of Congolese patients, and Jerry in 2021 conducted a study on the congenital malformation and manner abnormality in the Congolese newborn. And based on this experience, we were able to conduct this different developmental disorder study in DRC. And this talk, as I mentioned, is about the Congolese cohort of under 48 recruited probants. You can see as most of these probants was young children, and only one of them, the DNA quality was not sufficient for exome sequencing. So you can see at the end, we only sequenced under 47 Congolese patients with developmental disorder. This is not a trivial achievement in Central Africa, mainly for the DRC, because given our challenges for DNA extraction, for DNA shipment, and also for the genomic analysis. And the diagnostic yield of the DDD study in DRC of the under 47 probants was 43%. And the copy number variant yield was, as you can see here, 13%. This contrasts to the South Africa copy number variant yield of 60.2%, which is most likely explained by the lack of access to the copy number variant analysis in the DRC country. Amanda also mentioned it in the presentation. But the SNV's yield was 29%. But if we only consider the copy number variant negative participant, meaning that if you remove these 90 patients from the total number of the DRC patient sequence, the yield will increase to 35%. Also, in line with the other cohorts of DDD in the literature, the observation of the dominant disorder stand out as the most common causes of developmental disorder. And de novo is the most of them, as you can see here in this picture. For the copy number variance analysis, 22 pathogenic or likely pathogenic were identified in 20 individuals, and most of them were the deletion. And mostly for the deletion, you can see 13 was presumed, was de novo presumed to be de novo, and only 2 of them was unknown, the unknown inheritance. We explore a couple of factors, and also the possibility of this factor to influence the chance of reaching a genetic diagnosis. In the DDUK study, recruitment as a trio had the largest effect on the probability of the diagnosis, likely because this contributes to the identification of the novel pathogenic variant. In our DDD study in the seat of DRC, almost half of the participants were recruited as the duo, as you can see here, about 46%, mostly due to the father who was not available. In total, more diagnoses were reaching in the trio, but this was explained by the higher yield of the copy number variant, but not for the SNVs, as you can see here. The number of SNVs yield was the same in the duo and trio, but the copy number variant yield was higher in the trio compared to the duo. Okay. There was an excess of male, as you can see, compared to the female. Since this is observed in the most of the DDD cohort, this cannot be explained by the cultural elements alone, in the sense that boys receive more attention compared to the girls. This is why we see in the Congolese part. But this also can explain by X-linked monogenic disorder do not explain this difference, since more X-linked disorder was detected in the girls. As you can see, the result of the DDUK study here, that for the X-linked condition, 8% was diagnosed in the female. But remarkably, the diagnostic yield in the male was lower compared to the female, which also observed in the DDUK study. After performing a binary multivariable logistic regression, the odds ratio of reaching a diagnostic in the male versus the female was 0.3. Also, in the DDUK study, female was more likely to receive a genetic diagnosis than in male, but the difference were less pronounced. This data suggests that the explanation for the excess of male with a developmental disorder cannot be captured only by our current analysis of trio exome sequence. So we must go beyond of that. Amanda also mentioned the PCH analysis for the South Africa cohort. When we look at the severity of the developmental disorder, those with the mild developmental disorder were less likely to receive a diagnostic, as in the other cohorts of developmental disorder in the literature. In this group, where one could expect more multifactorial factor playing a role, represented only a few cases, and male were not overexpressed. So an excess of male in the lower intellectual disability group did not explain the lower diagnostic yield in the male. Those where the DDD severity could not be assessed as had a high yield. This group is for the newborn. As you can see, it was 15 newborn of younger children presented mostly the multiple congenital abnormality. where the degree of developmental disorder could not be assessed. And for the major congenital abnormalities, 63 of the under 48 proband recruited present at least one major abnormality. We recorded 24 different major abnormalities of this macrocephaly, clubfoot, and abdominal wall defects were the most frequent. The highest incidence of major malformation was seen in the youngest group for 0 to 4 years. Here it was about 3,248 individuals in this group. And the anomalies observed in the older group were less likely to affect cerebral. And indeed, the presence of at least one major malformation had the largest effect of a chance to receive a diagnostic, a genetic diagnostic, with an odds ratio here around of 6. Based on the clinical Gestalt evaluation, the Gestalt evaluation here was made by the consensus between the experienced clinical geneticists. And based on this clinical evaluation, this clinical Gestalt evaluation, about half of the individual was considered to be dysmorphic. Here I put just a couple of pictures of the individual that were recruits, and in the red shape is those one we consider like a dysmorphic, and the green shape one was the individual that have been considered like not dysmorphic. And likewise, based on that, the presence of dysmorphism has been considered like a major determinant of the chance of reaching a diagnosis. You can see 59% of dysmorphic individuals get a genetic diagnosis, and with a high odds ratio about 4. And these are some pictures of the patient that have been solved in this cohort. As Amanda said, we get some 3 patients with Noonan, 3 patients with Shank3, and also some patients with a common genetic disorder, as you can see here. We are going to talk about later about the patient with a dual diagnosis. As you can see here, this patient with the Singapore and the Phelan-McDermott, and this newborn also with the arthrogryposis and the 1q21 microdeletion. And we try to explore the value of this score in defining the facial dysmorphism. We know that Gestalt evaluation is considered to be rather subjective, especially for the unexperienced clinician. Therefore, attempts have been meant to use a more objective one that's called this score. This score has been generated by face2gene as a quantitative measure of face2gene, indicated the degree of facial similarity between a patient facial feature and those from the non-genetic syndrome. And actually, this tool is supported patient below 18 years. And we group, as you can see, the result of this facial dysmorphia is, but for the low score, patient is classified as not dysmorphic. For the non-significant score, patient is considered as uncertain. And for the higher score of similarity, patient is considered as dysmorphic. But we group the low score and the non-significant score as a non-dysmorphic to avoid a false positive. And we evaluated 144 pediatric individuals from the DRC cohorts in comparison with the Gestalt evaluation as the golden standard for the evaluation. Of the 69 dysmorphic individuals, 86% were scored as dysmorphic by the D-score and 14 notes. Conversely, of the 75 individual non-dysmorphic, the D-score was in agreement with 68 patients. So this yielded to a predictive positive value of 71% and a negative predictive value of 84% with a moderate F1 score about 0.78. So we performed the Kappa-Cohen test to establish the relationship, and we found that we found a moderate agreement between the D-score and the Gestalt evaluation with a Kappa-Cohen score of 0.53. So at that moment, face2gene is a promising tool, mostly to exclude dysmorphism in the patient that you recruit in your study. presenting, for example, developmental disorder, like for this one, and may help also in selecting patients for future genetic tests. In total, 57 different disorders were recorded in the Congolese patient, and the vast majority was observed once. You can see here 51, and 6 were seen in more than one province, and they are indeed very common disorder. In addition, as I mentioned before, we get 2 patients with dual diagnosis and two other one with partial dual diagnosis that I want to say something here. Regarding the patient with the dual diagnosis, as observed also in the literature, we know that 3 or 8% of patients have a dual diagnosis for the developmental disorder. But as for this girl with both a pathogenic variant in the SYNGAP1 gene and also in the SHANK3, the question was what the part of the phenotype is explained by each of the genes. You see, we put each phenotype here and we color each of them by a different color to see the similarity also and the opposite sign. The size of the bar shows the frequency of different features for different disorders here, and the colors represent in green features that are common in both genes for the SYNGAP1 and the SHANK3. In red are features associated with only one gene, and in blue are the features not observed in the proband. As you can see here, the most frequent feature is shared by the 2 genes here for this girl of 11 here. It is therefore not possible to attribute for each of these features to either genes. This is one notable exception for the regression for the SHANK3 one. You see the only red bar you can see here. Regression were seen in this girl at the age of 11. And this is a key manifestation of children with SHANK3 mutation when they grow up. For the second case with a dual diagnosis, you can see in contrast to the previous one, in this proband feature could not be clearly assigned to the MH3 gene causing the distal arthrogryposis. In part, this is explained by the fact that the 1q21 microdeletion is not a recognizable syndrome. And we got also 2 patients with probable dual diagnosis that we call partially solved patient with partially solved patient with maybe dual diagnosis. In these 2 patients, the variant detected explains some of the manifestation, but not the intellectual disability. This was our major key feature for the recruitment. So for this patient, we think that this leads us to believe that maybe this patient harbor or get a dual diagnosis, meaning that we have to go beyond the exome sequencing that we perform and get over for the genome and also for the APC, as Amanda also suggested mentioned in this presentation. So, like in conclusion, exome sequencing for in the DRC part combine the SNV and the copy number analysis has a huge potential as a first diagnosis test in the individual for an unexplained developmental disorder, also in Africa, but especially in DRC. So some challenging following the study are to translate this knowledge to from the research to the clinical practice, and also to share this expertise to the other African countries. But we starting by share or translate this knowledge to the clinical practice. You can see here in our reference center for diagnosed diseases by our consultation with some patient, but not only in the Kinshasa. You can see in the picture at the right of the screen are those patients that I want to see in the other provinces of DRC. But also we start to share the expertise. Amanda mentioned it in the international training program. We start by share this knowledge of the DDD, the clinical part of the DDD, but also in the the genomic analysis of data that we get for the DDD analysis study. So I want to stop by here to thank all the collaborators, all the funding, all the genetic laboratory, all the different universities that have supported our study, and also the proband and the family for the consents to show and to display the picture of their children. Thank you.
Thank you very much, friends. So this webinar has taken much longer than anticipated, but I think we still have time for a few burning questions. So any questions? You see there's a question from Alain. Is it an inbred subgroup? I'm not sure what you were pointing at, Alain.
It's for the PGAP3.
Yeah.
So shall I answer?
Yes, please.
So Ellen, they are not an inbred subgroup as far as we understand. So there's another question. So the South African, or the people of African ancestry who currently live in South Africa, we think are, well, we know are have moved into South Africa from sort of Western Central Africa. I mean, there may well have been some bottlenecks, and I'm certainly not a population geneticist, we haven't looked at it for PGAP3, but we have a number of conditions where we see common mutations, if you like, deep founder mutations on a common haplotype, and we think that they are sort of the results of, I guess, population events, and it is counterintuitive, but we do see them. So they are not consanguineous, they are not inbred. We have numerous examples, certainly in Southern Africa, of similar recessives with common mutations. I don't know that I know the full explanation, but it is interesting.
There's a second question about whether the data have been published.
So not yet.
Not yet.
Not yet, but the data have been uploaded in Decipher, because I saw you mention about Decipher. So all data for DRC and South Africa uploaded in Decipher. But I mean not have been free access and open.
Well, not free access yet, right?
Yes, we'll open the free access as the papers are coming out, which should come out soon. And also with the publication, we add ClinVar records as well.
Yeah. So, Prens, I think your PhD from last year, there is an embargo for 1 year, is it?
Prince, I didn't catch you.
So your PhD was published last year.
Yeah.
But
there's an embargo for 1 year. Maybe at the end of this year it will be realized. Yeah.
Yeah. Okay. So this will be available also. And then a question from Blanchard: whether you have found any syndrome specific to the African population?
In the DRC cohorts, not a syndrome specific to the African population. This may not be able to go beyond to see for some genetic candidates, but in my cohorts, not specific syndrome for African population.
But the question is also, I think the study design, the way the filtering was done, was not actually favoring the discovery of new entities, right?
Yeah, entities, yeah.
Because we used a set of DDD associated genes, huh? So that's the to-do list, I would say.
Yeah, I mean, I can answer it maybe not from DDD, and that is that we certainly have some conditions. So the two or three that maybe stand out for me as they're not specific, but they are far more common. We've recently published in the European Journal of Human Genetics our STAC3 data. So STAC3 is myopathy previously found in Lumbee Indians in North America, but almost certainly that variant is a deep, old African variant, and having been made aware of it, we now see it extremely commonly as a common recessive myopathy. Patients are homozygous, even though they're not related in South Africa. Fanconi anemia, there is a particularly common African FANC-G variant, again, a specific African phenotype. Huntington's, there is Huntington's 2, which accounts for about 1/3 of the African patients. So there are many other African examples, not specifically in the developmental delay space, but more broadly in sort of developmental disorders, there are a number of examples.
Okay. Then there is a comment by Alain.
Still to discover, yeah.
Then there is the comment by Alain on the CHAMP1 and POC EP signature. That indeed the CHAMP1 Foundation could be approached for other patients to confirm this finding.
Okay.
Okay. Any more questions or comments? So, well, if not, I would like to thank all the speakers of today, Nadia, Prince, and Amanda, for their wonderful presentations, and also for the wonderful experience I was allowed to share with you. And I think, yeah, we hope that we can expand our experience and include other groups from Europe that might be interested. So thank you all. See you later.
Thank you.
Thanks, everyone.
Can I answer a question that's just been asked, which I think requires an answer?
Yeah, it's common. It's not.
It's
not,
as common as it is in any other population. So
exactly.
It's completely incorrect to say that it doesn't occur or occurs less frequently. That's old dogma.
Okay, thank you.
Thank you, everyone.
Bye-bye.